And up next, we have finished with the electromagnetic spectrum. We're moving on to neutrinos.
Let me see if I can share this quickly.
Meanwhile, as he's pushing buttons, up next we have Marek Kowalski, who will give us an overview on the neutrino sky.
Okay. All right. I hope that works. Oh no, yeah. All right. Yeah. So I'm focusing in this talk on. If the sound is okay? Yeah. So thanks for the invitation and sorry for missing essentially the meeting until now, but I'm glad to be here. So I wanted to talk about neutrinos, but with a specific focus on sources that are also sources of pretty well established sources of gravitational waves, and all of this in real time, which is much of the focus of our own work. So it's a very broad field. So I drew this cosmic triangle here, which you probably have seen in one way or another. In the middle, in a sense, is the source that, in a sense, is the most prominent emitter of gravitational waves as well as electromagnetic radiation. And I would say also in neutrinos, although that's not yet established. So it's not the only source. It's actually, there are more other candidates. I mean, you can have a neutron star and a black hole, sort of whatever. Whenever you create an accretion disk, you will create shocks, and then it will lead to neutrinos. So a black hole and a neutron star will also work. Just binary black holes with an accretion disk will work. And then, of course, supermassive black holes with, each of them bringing their own disk with them, that should also produce lots of neutrinos. I'm not aware even of a prediction. I think that's something very interesting, but it's not something I'm covering today. In any case, it will evolve on much slower timescales. And then core collapse supernova, that's more speculative. In terms of neutrinos, I would say for sure for gravitational waves, that it has to be asymmetric in order to produce gravitational waves. Okay, why would we actually look at neutrinos? So each of the messengers bring their own sort of their own advantage. So, obviously gravitational waves, I don't need to discuss. Gamma rays, we've just heard. I mean, over a huge wavelength range, you can see, up to TeV, you can see these objects like kilonova, like a short gamma ray burst, probably. And also, of course, down to radio. So there's a huge amount of information you can get out of this. But what do you learn from the neutrinos? The one thing is, when I speak of neutrinos, I speak of high-energy neutrinos, so everything above a TeV, roughly. I'm not thinking of MEV nucleosynthesis neutrinos, which, of course, will also happen, but this would be much more difficult to detect. But these high-energy neutrinos, they tell us essentially about what's going on in the source in terms of, the very, very energetic material. So, there is probably going to be particle acceleration. Wherever you have shocks, you accelerate particles. And then this acceleration, we know this from other sources, can be extremely efficient and produce very energetic particles. And that tells us a lot about the structure of the object, the jets, but also magnetic fields. And so you learn a lot by studying these highest energies. Now, of course, you can also study high energies with gamma rays, but there is essentially a cutoff. It only works up to a certain energy. And so this is a picture of essentially how far you can see with electromagnetic radiation as a function of energy into the universe. So this is the galactic center, and this is the redshift of 1 or 2 roughly. And so the universe is, of course, remarkably transparent over many wavelengths. But once you hit a TeV, essentially the universe becomes opaque. And the high energy gamma rays scatter off background radiation, CMB in particular, And at 1 PeV, you cannot even see the galactic center with gamma rays. So if you want to explore this region, if you want to learn about the universe and also the sources of gravitational waves at 1 PeV, then you need to essentially find yourself a new messenger. And here we go. That's the neutrino we are talking about. Okay, roughly speaking, the universe is opaque to 1/4 of the spectrum, and we sure want to know what's going on in that in that last quarter. All right, so how do we go about? Well, we built gigantic neutrino detectors. I'm myself involved in IceCube, so that's shown here to the left, but there are others, Antares and CAME3net. CAME3net is right now, I think, the second most sensitive instrument, and it's still being built. So eventually, once completed, it will surpass the sensitivity of IceCube. I will today talk about IceCube results because they are simply more stringent, but also it's my project, but I think in the future, CAME3net will come out very strong and will hopefully dominate the field. So I already said what we can do with why high energy neutrinos are interested, but I want to say a few more things about. I just want to say a few things that. Let me start again. So let me put neutrinos in the context of those messengers, in particular binary neutron star mergers that we are most interested in right now. So we have, of course, there has been one coincident observation been made in 2017. And of course, we looked for neutrinos from that source too. I should say, and maybe I'll sneak in a little bit of information, these telescopes, like IceCube, they operate 24/7. And they look into all directions simultaneously. So there's no point, you don't need to repoint these telescopes. They point, there's no pointing. They register neutrinos from all directions. We are more sensitive at low energies if we look downward. But for the very high energies, upward is also okay. So if neutrinos come from above, then we can see those. At the highest energies, around 100 TeV or so, we start being able to tag individual neutrinos as being of cosmic origin. So when a neutrino at 100 TeV comes, we can give it a probability that it's of cosmic origin, and typically it's around 0.5 or higher. Okay, and so this is what we then use as alerts. Now, when we see a fantastic event like the neutron star merger in 2017, what we do is we go back to our data and we look, has there been anything seen? And the answer here is no. And it's not just no for IceCube, it has been also no for Antares, and it has been no for Auger. And you can see, the different upper limits here, Antares, IceCube, and Auger as a function of the energy, and this really extends up to 10 to the 11 GeV, so super high energies. And here you're seeing the models, and we're showing two models, one which is sort of plus minus 500 seconds before and after the neutron star merger, and another window is 2 weeks, so if just after. So we don't expect anything 2 weeks before, but 2 weeks after it could be because these things like shock acceleration, sometimes it takes time. You accelerate the material and then it actually has to reach sort of the target material to interact. So there are longer time scales involved, and so we usually think there's a prompt phase, and there could be something on a longer time scale, and we test both. Now the models for these two are shown here. So this is. The red are optimistic scenarios, and you're seeing that the optimistic scenarios, if the jet would point right at us, which it hadn't, we would be able to already exclude. But roughly, between maybe if we would have seen it, that neutron star, according to those models, if the jet would be 6 degrees away from us, it was 30 degrees, so that was too far. So ultimately, the limits are not saying so much. There's another set of models. It's called the moderate models, and I will be talking about those more today. And these are the blue ones. And the interesting thing is they peak at very high energies. So they peak at 10 to the 7 or so, 10 to the 8 GeV. Okay. So I'll be also talking about projects sort of that that go beyond what we are currently operating or building. So the step after IceCube, and that's called IceCube Gen 2. I just mentioned it here. It's an 8 cubic kilometer array, and it has a much larger radio array too, associated, so that we push sensitivity to the highest energies. And what you're seeing here, the sensitivity of IceCube Gen 2, it's very flat by construction because we are using the radio technology here to actually be sensitive, and it's in particular good for kilonova detection. So what you're seeing here are, these these delayed sort of emission on a time scale of 14 days. The model by Fang and Metzger, it really peaks beyond 10 to the 8 GeV. So almost, so extremely energetic. Could be the CAME3net event that was recently detected, actually. I think it's, we should think about, would we have seen it? And I provide the answer in a second. In fact, if you're not doing neutrino astronomy every day, you might not be familiar with a kind of an interesting feature of neutrino astronomy. I would really call it a feature. And it has to do with the fact that we are detecting individual neutrinos with very low count rates. Individual neutrinos that come in, just like the 200 PeV neutrino event from CAME3net. It's a single event. We are very certain that it's of astrophysical origin, but it's still only one event. So what do you learn about the source? Well, if you would have detected that source, what would you have learned about the source? And here it's important to remind yourself that it's actually Poisson statistics that drives this game, because there's not just one potential source in the universe, but there are billions of sources in the universe. And all you need is that one source has an overfluctuation. The mean expectation number from this source could be very low, 10 to minus 4. But if you have 10 to the 4 of these sources, one of them will actually produce a neutrino. Yeah, so the flux expectation is very low, and yet you see a single event. And we have studied this, and we gave it a name. We call it Eddington bias, because Eddington actually predicted this kind of bias already for optical photometry and optical measurements, and we thought it's nice to give it a name. So what you're seeing here is a distribution simply of of cosmic sources. We just simulated a bunch of sources roughly to match the IceCube observations, and we asked. And we in this case, but we did other cases too, we said it's blazars, yeah? So it's a cosmological distribution of blazars. And together the flux adds up to roughly what we are seeing in IceCube, okay? So, and then we asked, so where if you only see one event from that population, where does it come from? If you see 2 events and 3 events. And what you're seeing here is the flux expectation from that source. And you see, if you see only one event, then the median is a few times 10 to the minus 3. So you don't expect more than 10, a few times 10 to the minus 3 from that individual source. Now, if you see 3 events, we call this a multiplicator, 2 already. That immediately pushes the flux to that observed value. But if you only see one event, very likely you're seeing a very faint source. And so that can be translated to a distance. And so if you're just seeing one event, you're seeing the most likely spatial window is that this source is somewhere between a few hundred megaparsecs and a few gigaparsecs. So essentially everywhere in the universe. Yeah, so a single neutrinos, single alert sample the full universe. And so to me, it was not a surprise that I was not involved in the CAME3net analysis. I haven't seen the paper only when it was published, but I was not surprised that the counterpart was not seen because it comes out of this population. And if it would have been from a kilonova, the chances, if the kilonova explodes somewhere between 400 megaparsecs and 10 gigaparsecs, good luck. We would have never seen it. Yeah, I think there's no instrument in the world that would have seen it. It would have not even been detected as a gravitational wave, as a GRB, I think. So maybe it's, maybe for the moment, let's assume this is then the source, it's a kilonova of that super high energy event, and think about if we could have detected it. Okay, so this is just a little bit of background information. So let me spend a little bit of time now going to sort of how we are searching for, now the counterparts. If you are seeing a single, you don't know right away. You want to identify the source as quickly as possible, because otherwise, if it has connected to a short gravitational wave event, it's going to be gone. You're not going to recover anything anymore, right? The information is simply lost. So you need to be quick. So one thing we are doing is whenever there's a gravitational wave alert coming in, we actually go through our event database and we ask, do they align or not? And we create these maps. Here, it's important to understand the angular resolution of these events. The ice cube has a peak around 1 degree angular resolution. So the contours from ice cube are much smaller than the contours from gravitational wave sources. So in principle, the source confusion is dominated by the size of the gravitational wave contours. That will also become important. We have two methods that are being used, one based on a likelihood, a classical frequentist approach, one on a Bayesian approach. Both run routinely. We have, when we have data, you can go to this website, for instance. For every alert, you find our response. We make this public instantly, in order for the community to actually provide follow-up. So, you see the GCN knows this. If we see something interesting, any coincidence, then we actually add information here. And just in, let's see, when was this? In March, I think March 29, we actually did have an interesting observation. In fact, a lot of people freaked out for a moment. We found 2 neutrinos in coincidence with a gravitational wave alert. The p-value is 5 times 10 to minus 5. So that's already something that makes us, very excited. However, we learned through, internal communication channels that this was just a glitch on the LVK side. So unfortunately, I think it still hasn't been communicated publicly, but that's what we learned, and we felt we couldn't. Yeah, so our interest dropped quite a bit instantly, but we could not sort of take it back because our data is what it is. It shows the coincidence. If it's a glitch, it's too bad, but it wasn't. It should be mentioned by LVK, I think. Okay. Okay. So far I focused right now. I focused on. We have not. So I should have let go. Unfortunately, I cannot claim today. I should say this maybe upfront. A coincidence between a gravitational wave source and a neutrino source. And so what I've just explained to you resulted actually in so far no observation, just upper limits. And this will remain essentially for the rest of the talk. But I think the discoveries could be around the corner. So let's see, where should we look? So I showed you so far. I discussed this this approach to couple gravitational wave sources directly, which were observed in gravitational waves, for which there was an alert, to high energy neutrinos. Yeah, but there's another way. You can also go this way, and this is what I'd like to talk about now. And so we can, and it works because we essentially know at least how these binary neutron star mergers look like in electromagnetic radiation, right? If it's a short gamma ray burst, we'll be, we will be thinking this will also be a source of gravitational waves, even if LVK, if LIGO was down for a moment, it wouldn't matter. You would still believe that if it were up and if the source would be close enough, then you would have seen it. You don't need more. So, this is one example, but we also know how kilonova look like to first instance. And so we can also look for coincidences between neutrinos and kilonova. We don't need the gravitational wave signal to say something about gravitational wave sources. And that's what we want to explore next. And for this, I just looked through I don't think you had a talk this week already on the Zwicky Transient facility, so I just slide a little bit of information into this talk about the Zwicky Transient facility because we've been working on this. So, this is Mount Palomar, and there are 3 domes here. This is where the very powerful Schmidt telescope sits. This is maybe from my perspective, actually the least interesting telescope. It's the old. It's a big 4.5 meter telescope, and here is our 1.5 meter follow-up telescope. This is equipped with a with an SED machine with a spectroscopic instrument for rapid follow-up. And so what happens is, essentially, we discover sources here. We send this to this facility for follow-up, and that's doing the typing. Okay, on the inside of the P48, that's how it looks like. So here's the tube. It's a 1.8 meter dish. The aperture is just 1.2 meter because it's a Schmidt design. The camera is here. So at the time when we switched it on, it was very impressive. Today, I think it's maybe not so impressive anymore in terms of size, but it's still very, very powerful. And because it's a Schmidt design, we didn't know where to put the shutter, and we put the shutter outside so that it wouldn't block the light path falling into the camera. And as a result, the shutter is actually the world largest shutter, I think, until LSST turns on. So, and we built this at DESY. So this is the field of view of ZTF. So it's 47 square degrees. And here you see how it compares to other surveys. It's doing pretty well, even though it's already operating since more than 6 years. And I think but it's also producing lots of data, right? We're going through the night sky essentially once a night, and then we find lots of transients. And for this, we needed to build essentially tools to help us digest all this data. And one thing we have built at DESY and the Humboldt University is Ampel. It's a broker. There are many brokers, not too many, fortunately, but a few. It's not the only broker. All of them are slightly different. You have heard about Think already, and so this is just another broker. So what we are doing is, if we are processing the ZTF data in real time in the future, it will also process LSST data. And we are also processing IceCube data and gravitational wave data. So everything is coming together in this broker, and then we can see if there are matches. And if there are matches, we actually, then we start investigating. So one of the things we have been, of course, doing, and that's where ZTF is absolutely superb, is, of course, looking directly for the sources of gravitational waves. So if there's a gravitational wave alert coming in, we look for the counterparts. This is the sad summary so far. 0 kilonova after, in 2017, we were not yet on the sky, but we switched on in 2018. But we did, follow up quite a substantial number, and we have not found anything, so we can constrain the luminosity function. And so this is a plot from 03, so 04 until now has also not produced counterparts, and this is led by Caltech. What we have been doing is we've been focusing on the same thing, but now for neutrinos. So if a high energy neutrino comes in, we know it has a high probability to be of cosmic origin. We ask the question, are there counterparts? Do we see counterparts? And we then slew ZTF, and we actually observe it. And we've done this since many years now. And we've been following up roughly 35 neutrinos with ZTF. If we would have multiple sites, it could be more, but if there are few telescopes as sensitive as ZTF. So at this point, we are sort of 35% complete. And here you also see a little bit of statistics, how why we're not 100% complete. But I just want to show you one example of one thing which we found, which we are just about to publish. We are in the process of publishing. So in 2023, we found a nice high energy neutrino. We then slew the ZTF, and we went through searching for counterparts, and we found one supernova actually, and we classified the supernova then, and we are about to publish it. So it's this is the supernova. It's actually a very fast evolving supernova. It's not a kilonova because it's way too bright for this. It's a very bright supernova. It almost looks like an F-bot, but we don't think it's an F-bot. But in any case, this is a nice. It's typed as a 1BN supernova, so strip core collapse with circumstellar medium. We think it's very promising, but it's only one source, so we need to find more of those. So this is, I think, in terms of supernova, the most striking result that we have achieved so far. Now, I wanted to focus on real-time things. So I'm giving you essentially also dates for the work here. On Sunday this year, we have we have actually observed something else that was quite interesting, and it just shows how the real-time business goes. So, there was a high energy neutrino again. seen, but this was a spectacular neutrino. It was a 4 PeV. It's more than 4 PeV that was seen inside of IceCube. So it's a muon track with more than 4 PeV energy. So that means the neutrino is likely maybe 40 PeV. It's probably a factor of 10 higher in energy. So, a spectacular event. And even more spectacular, of course, if it is found in coincidence and spatial and temporal coincidence with a gamma ray burst, right? And that is what happened. So what you're seeing here is our IceCube contour, and what you're seeing here is sort of an approximation of the GBM contour. So there was a gamma ray burst roughly 100 seconds before the, no, I'm sorry, there was a neutrino roughly 100 seconds before the gamma ray burst. So we then, that, of course, when that happened, everyone was super excited. We then switched on ZTF. I didn't switch it on, it was on already, but we then sort of from Europe, it worked quite well. We were able to point it to this field. And the result is that we actually did find a faint counterpart. And we didn't know initially if this is real. It was just, but it turned out with X-ray follow-up that it's real, and it was the afterglow. And the afterglow, unfortunately, was not consistent anymore. It was still consistent with the GBM contour, but it was not consistent anymore with the neutrino contour. So it's 2 degrees. So this is our source here. And it's 2 degrees away, 2.5 degrees away from the neutrino source, and that's too far. We don't have that error budget. We think the contours are roughly 0.5 degree for this event, so we couldn't explain it. So super exciting, but again, unfortunately, not a signal yet. At the same time, it shows us that also we need to be fast. If we wouldn't have taken this observation, we would be scratching our heads until today. This way, we were, by Sunday evening, we knew, all right, let's relax, yeah. So this is why real-time work is so essential, because some of the information that you will not gain otherwise. Okay, all right. Now, coming back to this triangle, which of these two win? Okay, if you have two methods, you want to know which one is better, right? And which one is more sensitive? And okay, so this is maybe too complicated. I don't know for unless you're an expert and you have read our papers to this. We have just published 2 papers on this. But what we have done is we have done a toy model for how to stack sources. So when we say stacking sources, we mean you have a catalog of potential objects that could be the source, and you have the neutrino map. And then you correlate them, cross-correlate them, and you ask, in a sense, you put them all sort of onto the same coordinate, and then you ask, is there, from the combination, is there a signal? Okay, so that's what we call stacking. And if you do it very carefully and you make sure that you have very complete catalogs and you are not losing any information, that's what we call deep stacking. And we argue that in the past, people have not done stacking so well because, it was sort of a lot of information was lost in between. And we sort of worked out the math on what to focus on. But the one thing I want to say here and connect to my initial slides, remember, alert, single high energy neutrinos, they are found from sources everywhere in the universe, which means even though neutrino astronomy is not yet maybe so good in turning out so many sources, if we find sources, they are actually quite distributed. So we can actually study the cosmos over a very large redshift range. And we can also, if you gather the information in a consistent way, you can also use the information distributed over a very large redshift range to tell you something about the population. And what this is here is what we call the redshift dependent sensitivity for a combined search between gravitational waves and neutrinos. And we have different scenarios here, IceCube and LVK, so that's just 05, that's for essentially today. Then we have Gen 2, and nothing happens on the gravitational wave side. Then we have Gen 2, Einstein telescope, and Cosmic Explorer, which is, of course, the dream scenario. And you're seeing how the sensitivity changes, where the sensitivity comes from as a function of redshift. And the median redshift actually is pretty high, so you can find the sources at redshift of 0.3 or so will still contribute very significant to the to the result. at least if you do it in the combination of ET and Cosmic Explorer, because the pointing resolution is just so much better. Okay, here you see the cumulative distribution. So for the moderate neutrino signal in the future, we will have 10 sigma discoveries. If this model is right, we can expect 10 sigma discoveries. I'm going, if you actually look which combination of gravitational wave detectors should one use. So here you're seeing Cosmic Explorer and ET alone, but also Gen 2 combined with Cosmic Explorer and ET. Then actually, it's the combination, of course, that is the strongest. ET is the second strongest, and it's pretty much quite significantly better than Cosmic Explorer because it has better pointing. So if you do this cross-correlating stuff to discover things, pointing matters. And so you're actually having multiple gravitational wave detectors are good to have. Okay, and then finally, I think this is my last slide. So almost last slide. So you can also compare it, instead of comparing with gravitational wave detectors, you can do the same kind of sign searches, but with GRB detectors. So you switch off gravitational waves, you just look for the electromagnetic signature, and then you can compare the two. So here, IceCube combined with Fermi, Gen 2 combined with Fermi, and Gen 2 combined with Einstein telescope. The interesting thing is that IceCube and Fermi, that's this line here, is actually pretty significant. It's pretty nice. So we, in terms of sensitivity, we should be really focusing on gamma ray bursts. It can teach us a lot about also about gravitation, neutrinos from gravitational wave sources. Okay, final slide is just advertisement. I mean, I talked a lot about science, but ultimately behind all this is, of course, a lot of very good software. And that's also, I would say, the credit, or that's the reason why ZTF is so successful. It's very good hardware, but it's also excellent software. Sort of the pipelines really go hand in hand. And so in ACME, we want to improve, and we want to build a sort of an ecosystem that really works hand in hand. And so Fabian and I, we are leading work package 5. I just wanted to say there will be a face-to-face meeting June 12th and 13th in DESY in Zeuthen. And so this is how it really looks. And it's you should come and explore it. This is the new CTAO building for the data science headquarters. This is where we have, we will have our lunches. So anyway, come join, and yeah. And this is my conclusion, but I'm running out of time, so I'm just not reading it.
Any questions?
Yes. Hi. So I know you said you were only talking about the high energy neutrinos, so I'm going to ask you an awkward question now and ask about low energy ones. But the kilonova from 1708-17 obviously was relatively nearby. I don't know what the expected neutrino flux is, but there's lots and lots of nuclear synthesis going on. So are there any constraining limits, non-detections of like multiplots from 1708-17 at not excitingly high energies that you know?
You mean at MEV?
Yeah.
No, I'm not aware, but that doesn't mean it's not existing. But I'm also not, I'm very not interested because I'm not expecting anything. I mean, let's just compare it to, I don't think a kilonova will be per se much different from a core collapse supernova.
Okay,
but I'm not a super expert in this. But even for core collapse supernova at 40 megaparsecs, there would be at best, one neutrino in any of the detectors around. One neutrino means nothing. So you would have to, I think you would have to have the same object at maybe 100 kiloparsecs. So shifted by a factor of 1,000 or maybe 500. And then you would be in the regime where you can make a meaningful statement. So it's so far off the scale that I think it's, I don't know what if one can come up with a very beamed scenario it's unlikely.
I haven't done any of the maths in my head, so fair enough. While I've got Michael, can I ask you another really quick question? For the high energy things, because the alerts that come out where we try to follow up like with Swift and stuff, the errors in them say it's statistical only. What is the typical systematic error that one should factor into that as well on your high energy positions?
I mean, we report with systematic errors. So IceCube is reporting with systematic errors. Maybe the initial alert not, but when we do the marginalization, it actually includes systematic errors. We don't add we actually don't ask for, we don't add any systematic errors, but what we do, yeah.
Okay, the notice thing just says error stat only from the GCN notice at least.
But which one? Is it the
this the one I've got on my screen is 250309 because I was just checking what follow-up we've done. We can talk about that offline. It's fine. I was hoping you were going to say like 0.2 square degrees, and I was going to write that down, but
no, that's
Yeah.
not. I think usually what we do is we have one very quick follow-up, and then we have one later, and the later one should, in principle, the methodology, it should actually include the systematic error.
Okay.
Now I check. And I can
It
see
might
if
be
it's
GCN ingest issue. They might add those words. Yeah, we can talk
Yeah.
about that offline, but okay, thank you.
Okay, thanks. I think unfortunately we're out of time for this session, and I believe we have an extra short coffee break. But first, let's thank Marek again.